Okay, let's start for the last day. I think there are two interesting, hopefully interesting talks for you and some exercises. Okay, overnight, the snow, what we discussed yesterday, became wet. And I continue actually there where we stopped yesterday. And I tried to introduce you a little bit the state of the art, some basics, and where we are going towards monitoring snowmelt area and wetness from synthetic aperture radar data. Very quickly on the outline for the next 60 minutes. So we have to review the dielectric properties and signal presentation of wet snow and refrozen snow. So I think this somehow comes together because snow is very dynamic. And we have melting during the day and refreezing during the night. And this, of course, is a strong signal. Then I show you some data on backscatter signal from wet snow. We discussed this quickly. So we are not going through the dry snow. So I hope that you remember how it behaved for dry snow, the different backscatter processes and contributions. Then we talk about the evolution of a backscatter signal during the season or during a period with warming and refreezing. And then I introduced you to a couple of methods that are used for monitoring snowmelt area in mountain regions, especially in the Alps, with some examples. But I included for our Icelandic friends also some Icelandic slides, a really fantastic place. And then we switch also a little bit to polar regions to look for the melt processes on ice shelves and ice sheets, which is also applicable to glaciated areas. At the end, we will introduce a quick overview, because everybody is sitting here together, to the plans for the exercise, which starts immediately after this talk. So there will be two parallel groups, and Gabi, she's not here, yeah, she should be here, will help me on that, and she did a lot of work in order to prepare it. You will get handouts at the entrance of the computer rooms. And then I hope that we finish, and I give you also some references for further reading. Okay, let's start with the basics. So we have the microwave permittivity of ice and snow. And when we look for, so we have a real part of the permittivity and an imaginary part. And the imaginary part is responsible for the absorption of the microwaves in this part. For ice, for example, the real part is quite constant in 3.15, so that's a number. It depends a little bit on frequency and temperature, but in principle 3.15 is a good number. And the absorption part, so the imaginary part of the permittivity is super small. So it's in the order of 10 power minus 4. So therefore, when we look for frozen ice in the Arctic or Antarctic, or also on glaciers or dry snow, it penetrates quite a lot. For dry snow, so this is for ice. When we look for dry snow, we can model this as a kind of function of the density. We see here these formulas which were actually taken or derived from a lot of measurements in different regions, and they hold in principle for all these typical dry snow regions. For the absorption part, actually, it is also quite small. It depends in principle on the ice, so it's super small for the ice itself. And then, of course, we have also a correction term for the density, because this is the packing of the ice crystal. So the denser it is, it increases slightly. For wet snow, this changes. So it is based, so the model, also based on a lot of measurements, says that we take the dry snow part, and then we are adding a correction term, and this is the volume fraction of the liquid water, so really the liquid water content in the volume of the snowpack. And then it depends on the frequency, and then we have also a relaxation frequency there for normalization. So this is the Debye frequency. By the way, it's about 9 to 10 gigahertz, so that's a value which has been determined. And when we look for these parts, so the dry snow would be here. But then we see, of course, that the real part of the permittivity, which is responsible also for scattering and so on, depends on the liquid water content, so it increases. So we have here a range from 0 up to about 8% of liquid water content in the volume, which is quite wet snow. And we see that it's frequency dependent. Blue would be L band, C band, and X band. And, but the changes in principle, we are still in the same order of magnitude. For example, for 4 or 5% in this range, it changes for dry snow from a little bit below 2 up to about 2.5 or something like this in this range. When we look now for the absorption part, there's a dramatic change when we have some liquid water in there. So this is also the case. And when we go here, so in principle, we have it for dry snow very, very small, in the order of about 10 power minus 1 minus 3 or power minus 4 in this range. But then we see immediately that for 4 or 5%, we are going up to 0.5 in this order of magnitude. This is a dramatic change by a couple of order of magnitudes. So the microwaves have a strong interaction with the liquid water, and this is caused by the dipole order of the water molecules. They are starting to rotate in the water. So this is causing the absorption. And this, of course, has an impact also on the penetration depth. So the liquid water takes away the energy from the microwaves. We can calculate the penetration length. So this is in view direction of the radar signal. It depends, when we look to this, it depends on the wavelengths, in principle on the frequency, and on the real and imaginary part on this one. And that can be calculated, of course, again, for a snow density of about 400 kilogram per cubic meter. I showed here for different frequencies, L, C, and X band. These are the main frequencies where our satellites are currently operating. And we see that, again here, the liquid water content from dry to about 8%. And the bluish would be L band. So we are going down from a couple of tens of meters penetration in the dry snow case down to 1 meter or less. This is one-way penetration. If we have a backscatter signal, then it's divided by 2 in the order of less than a meter or half a meter in this range. So that's a dramatic change, of course. So we are getting, so you have to imagine if you have 2 meters of snow, then we have, and it's wet, completely wet, then of course this is in principle absorbed after a couple of wavelengths. When we look for C and X band, here we are much, the penetration is much smaller. So at C band, for example, at about 3 to 4, we are in the range of the top layer of the snowpack. That's about 5 to 10 centimeters in this range. So for 2 meters of snowpack, we just got most of the information from this top few centimeters. At X band, it gets even less. So all the signal is coming from the top layer. It depends on the wavelength. Therefore, of course, when you remember yesterday, when we were looking for the single pass interferometric retrieval of the snow height by DM differencing, we wanted to have the surface. And then, of course, penetration is nasty. We want to avoid it. And this is the reason why we are going for the wet snow part, if possible, because the signal is in principle limited to the top layer of this. And then, of course, when we go to Ka band, this is even worse. So we are really at the surface in the top millimeters. So when you deal now with the discrimination of dry snow and wet snow, also with microwaves, always remember this, that once it starts getting wet, then, of course, the signal changes, because it's the same on ice sheets, on glaciers, and also for the seasonal snow. So from the volume contribution, this is reduced primarily to the top layer, in principle, depending on the wavelengths. Now, but this is a fantastic thing, because that helps us actually in order to detect when the snow starts starts melting. So this a small amount of liquid water in the snowpack can help us to discriminate between the dry cases and the wet and case because of this strong absorption in the snow itself. And we did some measurements on this. That is the Leutasch region. So we made this 20, 30 years ago. It's close to Innsbruck, 1,100 meters, excellent for cross-country skiing. And this, you see, the snowpack, it's a cultivated meadow, a very controlled experiment. And we did a lot of, we had snow temperature measurements, also measurements in the ground to see how the ground conditions are. And what we did is continuous measurements all over the season. So starting in late autumn, and we did it at sea and X-band, actually, at co and cross pole. So we added together HH and VV. They are very, very similar. They were just average to have a better estimate. And the cross pole would be HV or VH, also averaged. And the range here is a little bit big, so it's from +10 to -50 dB. This is an extreme range, actually. When you remember for Sentinel-1, noise equivalent sigma 0 is about -25, so that would be here. Terrace X would be about, actually, -20. So for wet snow, when we look now to these numbers, and this is the incidence angle, the look angle, and this plays also a role. And when we have actually, let's compare it and start with C-band. So the green one is the meadow, of course, the meadow is green. The bluish one is the dry snow, and the wet snow is red. And when we see that at lower incidence angle, at C-band, so I look down with 10 degrees, very steep. They are very close to each other. It's hard to discriminate. When we go to 20 degrees or more, then there's a significant difference. So this change is in the order of 8 to 10 dB. That you see by the eye. You don't need to be an expert. The image, when you look to the SAR image, I show it later to you, it is dark. Okay, so backscatter is a big change. When we look to the cross pole is in principle, in general, much lower. We cannot discriminate, and you see here, we cannot discriminate, in principle, the meadows and the dry snow. So that is the snow-free case and the dry snow case. There's a small difference, and the difference is caused actually because of the insulation of the snowpack. The ground below might change during the season. It's not the same as in autumn when we did the measurements. And this change has some impact also because dry snow is transparent, as we learned yesterday, more or less at C-band. And therefore, we have also a very big change. So this is 10, 12 dB between the dry snow and wet snow. And the big advantage is I have a lower incidence angle at about 10 degrees or 15 degrees. It's a very good discriminability between those. It's not the case as in the cross pole. And of course, when we look also to the magnitude of the difference, here it's about 5, 6, 7 dBs in this range. And then of course here it is much stronger. At X-band, it is in principle the same figure. So we have a problem a little bit at steep incidence angles. But when you look to the magnitude of this, X-band is a little bit higher because we have also, for the dry snow especially, but it goes quite narrow down. Then of course you were asking what is the problem with the cross pole? Why are we not using it? The cross pole has very low values, especially for these smooth surfaces. I come later to the impact of roughness, but for smooth, when we have a winter snowpack, undisturbed, and then we have the first sunshine and snow starts melting, then we have the first liquid water in the snowpack, it penetrates into the snowpack, and the surface roughness is not changing and it drops significantly. The problem with the C-band and X-band is that we are quite low, especially at the lower frequencies, so we are at -30. And here we are coming to the limit of satellite systems. They have a noise equivalent sigma 0 of about -25 approximately for Sentinel-1. In some parts of the swath it is a little bit worse, so it's -21. And when we are designing a satellite missions, we are always pushing that the noise equivalent sigma 0 is going down. Everybody likes this, because then we have a good measurement. If a measurement is going towards the noise it is not really reliable anymore. So the noise plays more and more a role. You need the noise correction. If you are far away from the noise does not play a role. So if we are here, for example, at about 10 dB, then we have to see this. And sometimes this noise equivalent signal 0, to make it down, is a kind of budget cost for satellites. So they have to increase the amplifiers and so on. Now, so we can discriminate this. And now we did some modeling. So what is the impact when the snow starts melting? First, it's completely dry, and then it's the first sunshine. Then we have a little bit of a skin layer, which is wet. This might refreeze over the night. And we calculated now the impact of the wet snow on top of a dry snow. So this is this sketch here. So we have a certain thickness of a wet layer. This can be snow of 2 meters, and the first 10, 20, 30 centimeters are actually wet with a certain amount of liquid water content. Normally, of course, this has a kind of gradient. In this case, we assume that it's a homogeneous amount of liquid water content in this layer. And this is on top of the dry snow, and below somewhere would be the ground. It's not shown here. What happens if I have the starting of this with 1% liquid water in the volume? Then we see that there's a decrease, of course. When the thickness of the layer is, let's say, 10 centimeters, there's a small change in backscatter. And if I have 30 centimeters of this, so on the x-axis you see the thickness of the layer, of this wet layer, and this would be the backscatter. Then there's a small change for this one. So I have still some interaction with the volume. When I increase this to 2, 3, or even 5%, so this is already getting more and more wet, we see in principle I have a dramatic increase. So after 5, 6 centimeters of 5% of liquid water content, even if it's below dry, we have a dramatic decrease to this. Afterwards, if this gets thicker and thicker, it's already saturated. So it doesn't matter anymore. So this first 5, 6 centimeters of a wet snow layer is taking all out of it, and is in principle masking out what is going below. So I cannot get any information out of this. I have a little bit of information when the liquid water is very small, but when it gets wetter and wetter during the melting season, then of course I get only information of this up one. Of this upper layer. So this would be the top. In principle, always remember, it's in the order of the magnitude of the wavelength when you have really wet snow. So it's for X band, it's 3, 4 centimeters. For C band, it's 5, 6 centimeters. And this is calculated for C band. And when we are looking now, just to reverse it, what happens when we had now a very nice day, as we had it on Wednesday, and then the night comes, temperatures are dropping below 0, and refreezing starts, caused by the cold air. And we have refreezing from the top downwards. So in principle, we have now 3 typical layers. So it's a refrozen crust on top of a wet layer from the day, on top of the dry snowpack. It can, of course, the dry snowpack we don't need. It can be all the snowpack very wet in May or whatever. But in principle, this is this sketch what I showed here. And this refrozen snow overnight, or if you have a cold period for a few days, this is increasing in time. And this is shown actually here. So we have different scattering contributions from this part. So they are shown here. So we have a contribution from the refrozen layer, also from the surface in this way, then from the volume. It penetrates because this is dry snow, but it has bigger grains in principle because it has clusters and so on. Then we have the wet snow. This we have liquid water and ice crystals and so on in there. So this is there we have the strong absorption. And if this is only very thin or has not so much liquid water, I can still get some information from the dry snow below. But that is in generally quite small. And when we look to this, so this is again a model actually for this at C band, and we see, for example, so that's from -12 to about -22. So there is no refrozen crust at the beginning, so completely wet snow. And I assumed here liquid water contents for the snow layer of 1% and 3%, corresponding to the solid and the dashed line. And for 3%, you see that we are quite low when we have the complete wet snow. It's about minus 20, 21 dB. And that's, of course, causing now that I need the right system. If I would have a system which has a noise equivalent sigma 0 of only minus 15, then I would have already problems in order to measure this. So we, from the design of a mission, we try to make this as low as possible. And then we have the refrozen crust increasing to about 1 meter, so that takes some time until this is done. But we see, for example, that we have continuously, when this refrozen crust is forming and getting thicker, we see that backscatter is increasing. So for 20 centimeter thick crust, it changes from about minus 20 to about, let's say, what is it, minus 18, minus 19 dB in this order. So this is already a significant change, what we can measure. Just as a background, Sentinel-1 has a radiometric accuracy of 0.3 dB. Everything what is below is a little bit unsure, but when you look to this 1 dB change can be measured quite well. And then, of course, if this increases, what is the case, for example, for polar regions, because there we have not only day and night, but there polar night starts, and then we have a continuous refreezing of the wet snow in the margins of Greenland or Antarctica, then, of course, we are going up, actually, relatively to high values. And this we can observe. In the 80s, actually, Christian Metzler and Reber made an experiment overnight, and this I want to show because this is a really unique and interesting measurement. They measured continuously with a ground-based scatterometer at X-band in this case, every couple of hours the backscatter during the day and during the night. And this was in 8th to 10th of May. There was some melting during the day and refreezing during the night, and they measured by hand the thickness of this refrozen crust to see the impact of this. And this is very interesting because we see that, for example, at 10 o'clock, everything was wet from the surface. Then this is 3 in the afternoon, then the night starts at 8 in the evening, then we are here close to midnight, and then morning again, 11, so close to noon on the next day. And here we are in the afternoon, and then the evening starts again. And we see the thickness of the crust evolving overnight. So, and the thickness, if you see the numbers, so these are millimeters. So this is about a crust, in this case, of about 200 millimeters. So this is a significant crust, of course. And when we look to the backscatter measured on this, so this is gamma, so we, in one of the next lectures I transfer this to Snowmelt, but we see that we follow more or less very nicely this formation of the crust. So this, and why is this interesting? The formation of the crust has a big impact on the surface energy fluxes between the snow and the atmosphere in both directions. And this is, of course, of very interest for meteorological models, snowpack models, and so on. But we see also that this is a highly dynamic process. So it's not that one measurement per day somewhere can give me information on this. What I would need is to sample, in principle, very accurately, every couple of hours, the information on this. Now, we talked now about permittivity. So roughness is not changing. But everybody who goes skiing or out in the field, we know that at the end of the melting season, the snow itself gets rougher. So the snowpack is retreating and we get some surface roughness. And this was a discussion actually, how big is the impact of the surface roughness, especially for wet snow. And we made an experiment on the glaciers actually during ERS campaigns. So this is Kesselwandferner, 3,200 meters elevation. So between Kesselwandferner and Gebatschferner. It was a super smooth surface somewhere in August. So we had no surface roughness. There was still a lot of snow. It was the good times actually. So this was in '92, so 30 years ago. And we made an artificial roughness field. So we said, okay, everything is smooth, and then it took us about 2 hours or 2.5 hours and a couple of beers afterwards in order to make this 100 meters, 50 meters wide. It was ERS, pixel size was in the order of 20 meters. So we were walking and walking like this. And at the end, of course, it was not a perfect roughness field, but we changed the roughness of the snowpack. We measured the roughness. So this we just walk with the skis like that, okay? A little bit boring, but okay, we did it. And we measured the roughness with a laser profiler. How you measure roughness, there are different techniques. One is that you have a laser, a profiler, you stand it up, and this should be horizontal, and it measures the distance, and then you get a profile like this. Every millimeter, in principle, you get the distance from the rail. And you can do some statistics with this in order to characterize it. But this looks like we were walking across this. When the aim was, when we are looking to glacierize, a very similar pattern appears, because we have this drainage of the water down there, and it looks in principle, so that's Hintereisferner, also in the lower region, the glacierize, and we see a similar pattern. So these channels, it's going up and down. I think on many glaciers this happens when we have this surface runoff. These are just these smaller runoff channels. And then we had this ERS image. These are corner reflectors, what we set up for calibration, and this would be the roughness field. And compared to the surroundings, actually, we had about 18 dB, 17 dB change in backscatter. So this is super big, I would say, super strong. We have to say that it's not a random roughness, it's a kind of periodic roughness, because it would be better to have a kind of random roughness. It's the same, but okay. It should just demonstrate that roughness is the second process for wet snow, what we have to take into account. And this is a kind of, yeah.
When do you consider a surface as rough compared to your wavelength?
It depends on the wavelength, yes.
Yeah, but what's actually followed? So when would you say it's smooth surface, it's rough surface?
Yeah, okay. You make measurements like this, and then you take the standard deviation divided by the wavelength or the wave number, and then you get a certain number. And depending on the model, what you use, so there are various types of surface models, which take singular roughness or other roughness measurements, parameters, and then the model actually is valid for a certain range of roughness. Some are more for smoother surfaces, some are taking in account, accounting for these stronger roughnesses. Normally models are not taking account, or cannot model like this. That's super hard. But normally we try to model, or what typical models are, this type of roughness can be taken into account of a couple of centimeters in the standard deviation. It's not that the model takes these values. Normally what you calculate is the standard deviation of the height versus the mean over this rail. And then another one is the autocorrelation, which is important. So this depends, gives you information on how, if it's really random or if you have a kind of periodicity in there. But the model, in principle, the general model used is a IEM model from Fung and so on. So this is a kind of classical model which is used to use it. There are also simpler models, geometric optical models and so on, which can be used. But in principle, they are always valid for a certain range of roughness. So they specify this. If you go out of this roughness type, then you get crazy values. But it shows that this type, and then of course, when you have two things which can change. So one thing is, of course, the permittivity, so the liquid water content. On the other hand, during a couple of days, especially when, for example, rain falls on the snow, then also the roughness can change. We have one measurement in principle. From where should we know finally what is changing? So we need to do some assumptions on that, okay? So this is kind of what we have to take into account. So we are measuring the complete change of this, so roughness change, but also the change in the liquid water content. Okay, a kind of memory, so you can take your smartphones, but you get this anyhow. For wet snow, it's just to summarize this: surface and in some frequencies also volume scattering is important. The liquid water content in general is the dominant parameter. Surface roughness for most of the frequencies. This is really important. Surface roughness is important in X and lower, so C band and L band. So this we have to take into account. For higher frequencies like Ku band, but also Ka band, for example, the grain size and clusters play also a role. Dry snow, we discussed yesterday. I added here now the refrozen snow, this crust in principle. And here the main part is the volume scattering contribution. So we have, and when you look, when you go out sometimes and look to a crust like this and to the snow below, just take your time and just take a little bit of this. It is totally different, this refrozen crust, especially when it has refrozen a couple of times. On the grain size, on the shape, on the clusters, there are ice lenses in there, even pipes can be found sometimes. So it is really different from a normally dry winter snowpack which has not been melted before. And what also happens is, of course, that we have internal interfaces between the snow layers because they can have different, for example, there was a melt and we are adding some fresh snow during the winter season with the density. This can be also melting, and then we have this typical stratigraphy. And these internal interfaces are also causing some multiple reflections. So I'm not going into detail, just you know, it's a little bit more complicated, that you have to account for these multiple reflections between the different snow layers. And they have also, of course, an impact, especially when we go to regions where we have this very nice stratigraphy in Greenland, percolation zone, or in Antarctica, where we have really or even on Icelandic glaciers, you can find this. And there are also electrodynamic models who can at least partly take care on this. So you can build up a snowpack with the different properties. But for every of these layers, you have to specify these parameters, which are so liquid water content plus grain size and so on. Okay, now the interesting part. So we know now the theory behind it. I show now some examples. So this is X-band. This is the region, so Hintereisferne, one of these regions, I think it was introduced also before. It's in Ötztal Alps. That we had the roughness test field was about here. That this is Kesselwandferne, and this is actually the big one is the Gebatschferne. This is 25th of December 2008, in the middle of the winter. Everything is refrozen. Backscatter is high. Why? We have big grains, large penetration, and of course we have fern areas in this region, and the grains are big, so we have effective volume scattering effect. 10th of July, okay, if you have heard the last two lectures, then you know it's a dramatic change, okay, of a 8 or 9 dB. And what should it be in July? Of course, this is wet snow. In principle, when you look to it, you can detect it by your own eye. You don't need to be a professional. If you know that wet snow has a low backscatter, you can easily see it. We need a technique, actually, automatically, to map this. And this is one example. At X-band, what we can get is the wet snow extent here in red, a little bit unusual. And this would be the layover regions in yellow, where we have no, due to the SAR imaging geometry, we have no information. How are we doing this? This is now Sentinel-1, and here we see one Sentinel seen over the Alps. It's in 22nd of April. And when you know that this is the Alps, you see immediately where the snow is wet. So, okay, I need not to tell you. It's, in principle, a super simple task to make a procedure in order to get a map, a binary map for the wet snow detection. So I will quickly go through this one. That will be one of the, or that will be the exercise for you in half an hour. So now you have to listen. So we have two images. One is the snow image acquired with the wet snow, and this would be the reference image. Why are we taking a reference image? When you remember to the very first one, we have an incidence angle dependence of backscattering. So when we just, when we look to the Alps, we have back slopes, so the incidence angle ranges from 80 degrees up to 10 degrees. So the full range what we have due to this topography. And we have to take out the incidence angle. So you cannot just take the image and make a threshold and say everything below 5 dB or minus 5 dB is wet snow. It's not working out. Because when we go back here to this slide, we have here a decrease of this with the incidence angle. So if you select one, you can say, okay, some regions will be wet snow, some will be not. So when we are taking a reference image acquired at dry snow conditions or snow-free conditions where, and average this, then we can take the difference between those, or the ratio. A difference in dB is the same as the ratio in natural units. So we talk about the ratio. When you calculate it and you have the values in dB, just make a minus. So that's a good tip. And then, of course, they are co-registered. We co-register them accurately. Then we can apply some multi-channel intensity filter. This is because we don't want to have the speckle. I come to this back later. We are calculating the ratio between the snow and the reference image in both parts. We can actually fuse this. And depending on the sensor what we have, we can apply different combinations of this. The most simple one is for ERS1, NVSAT and RADARSAT, where we have only one polarization, so VV in this case. We just take VV of the snow image minus, or the ratio with the VV of the reference image. Then we take out most part of this incidence angle range, and actually we can then threshold this by a constant threshold, what you derive in comparison with Landsat data or other information. But it's quite stable in time, so we tested this over different regions. Then, in principle, you can geocode this. You can do the segmentation and post-processing, so you remove forested regions where the signal is masked by this, by the trees. And finally, you get a kind of snow map, and then you can even merge different tracks in order to increase the observing region, because the Alps, you need a couple of tracks, and then you can see this. On this part, you see, for example, when we're having the ratio of snow-free versus the snow part for a couple of regions, so we made the statistics here. You can discriminate it quite nicely, but we know that at VV actually we cannot discriminate it because of the signatures we have shown before. And for this we are actually using the cross-pole one, where this discriminability is quite good. And therefore we extended this very simple approach to combine it. And the basic idea is that at lower incidence angles, below about 20 degrees, like this, we are only taking the VH. The VV is not really useful. Afterwards, we are weighting the VV, so with increasing incidence angle, the VV is taking more and more parts on this. And at the end, of course, so at very high incidence angle, the VV is a little bit better because we know that we are going with the VH, or it could be that the VH is going towards the noise of the system. And this is a kind of combination what is done here. So I think you will do this also in the exercises. The weighting factor is calculated by the incidence angle, so we have in principle first the VV, then with the increasing weighting factor with the incidence angle, what you can get direct from the imaging geometry. You can calculate this value K, and at a certain K then K is a constant value. This idea was in principle slightly modified. You can adapt it, and I will not go into detail here. But another very interesting approach is that it's almost the same starting point, but the calculation of the weighting function can be different. How you combine this cross-pole ratio and the co-pole ratio, that can be different. And in this case, so Manicam and Barros actually used a different lens surface type map in order to adjust this. So it's dependent not on the incidence angle. You can use also this dependent on the lens surfaces in order to adjust, in principle, the weighting between these both values. Now, a reference image is a critical part, I have to say, because if the reference image is taken at the wrong snow conditions, you have a problem because the ratio will not give you what you actually want. You want to have the difference snow-free or snow-covered versus the wet snow part. But to find a larger region where this condition is given for one image, this is really hard to find because we know Snowmelt can be in the lower part, but the upper part is still dry. So this is not really suitable. On the other hand, we can have also variations in soil moisture and vegetation and so on. So this was always a kind of tricky thing in the times of ERS and Envisat, where you had only a sparse sampling in time to find the proper image. But now with Sentinel-1, we have a continuous time series, we can really make a kind of brute force method. We are taking, in principle, 20, 30, 40, 50, 100 images, how many are there? And they are there. We have 10 years of Sentinel data, every 6 days acquiring in repeat pass. We can, we select in principle a potential time period where we expect that there is snow-free in late autumn or dry snow in the early winter season. But it could be also that there is still some melt, but we don't care. And then we are co-registering this, and actually what we do is to look for, on the pixel by pixel basis, on the statistics of these 30, at least 30 measurements or 100 measurements. And then we can look to say, okay, if the backscatter is low, it might be melt, I'm not interested, I remove this. And then I'm just averaging, in principle, the upper part. And this is a quite good approach, because first you need not to do it manually. So this is not a nice thing to look to hundreds of images to find it, and that's always a problem. You just need the images and just do some processing for a day, and then you will get a very nice image. I show you how this works. Iceland now. You see, this is, I think, from October, a couple of images. Overall, these are 48 acquisitions. You see the movie of the individual acquisitions, and you see how backscatter is actually changing. Now, if you ask, you select the proper image actually as a reference image is not so easy, because you look to 100 images and say, maybe this or maybe this. It's a kind of gambling, I would say. So you can use all these images, and to apply the method before, you get actually an image like that. And I zoom in now to this region. Then you see, first, the advantage is all the speckle is gone. I'm averaging 20 images in principle, or 15. And then, of course, I see all these different land surface types, and it has a typical characteristic backscatter at a certain incidence angle of this track for this region. So it takes away or averages away all these parts, but extreme events like big soil moisture floods or wet snow or whatever happening, these are cancelled out by outlier removal and so on. Speckle statistics, it's important. Why? SAR is a coherent system, we have speckle, and when we look to a single look image, so Helmut has shown this, we have always these a little bit noisy images, if you remember. When you form the ratio, actually, between two single look images, this speckle effect is even enhanced, and this is nasty. And therefore, the aim is to get as much as a good estimate of the backscatter of the pixel, without the speckle effect. There are two techniques what you can do. One is to do multi-looking. This is the correct approach. You take 10 times 10 pixels and average this with the intensities, or the backscatter, so not the amplitude, the intensities. And then you remove the speckle a lot. What is the disadvantage of this? The disadvantage is actually that you are losing spatial resolution. And therefore, you can apply a speckle filter. When we look here to the PDF of the backscatter ratio at 6 looks and 16 looks, And the difference would be from minus 4 dB to, the minus is missing 1 dB. Then we have in principle this distribution, and when we apply a threshold with 6 looks, I see in principle these misclassifications here. So the threshold, so something what belongs to this class is actually by the threshold moving to that class. And you cannot avoid this. The only thing is what you can do is that you are increasing the number of looks. With 16 looks, you have only a smaller part. So the aim is go up with the number of looks. And this is kind of trade-off. What is a typical resolution, what you need in the product? In my opinion, I prefer the multi-looking, so the averaging. The advantage is that you know the image statistics behind it. Once you're starting with filtering, like gamma filter, frost filter, or whatever, these typical spectral filter, the statistics behind is not known anymore. Why is this important? For a classification, I can calculate the probability of error independent of the number of looks for a distributed target. And this, for example, shows you when we have a difference of, let's say, 4 dB between two classes, and we have this, let's say here, 8 looks. Then, of course, I have already, you cannot avoid it by this thresholding technique, a probability of error of 25 or what is it, 15%, I think. You can just look it up. You cannot avoid this. This is in the nature of the system. This is speckle. This is, if you go to a soccer field and observe it with SAR, then you will have that amount, 20% of the pixels are just wrong. They are not wrong. This is the nature of the system. The point is now that we have to go up with the number of looks. For example, when we go up here to about 128 looks, so bigger pixels, then of course we have only 1%. So some of these parts. Oops. Okay. Finally, we get something like this, what you can produce today. We will have this bluish colors is the wet snow. That's a time series of Sentinel-1. Innsbruck is here. We were somewhere in this region, in the glaciers. And here, actually at the very high one, during the early season, we see these cyan colors, which is actually the dry snow, and that you can fill, because we know in mountain regions it is up there. You can even use an optical image for that if you have it. Iceland, when we apply this, what can we expect in the accuracy? This is an intercomparison of a Landsat image with the Sentinel-1 image, with the different techniques. So we get an accuracy or agreement between both of about 97%, which is excellent. Normally it can be a little bit less, depending on the part. Where are the main differences? We expect the main difference is close to the snow line. Why? At the snow line, the snow is in general rough, because it's breaking up. And therefore, the optical image is detected, while SAR, due to this roughness, the backscatter goes up, as we have learned before. And here we have the problem in detecting it. Another example here in Ötztal region. And again, here it's about 96%. In general, I would say if you get a 90% agreement, it's quite good. When we go away from the mountains to the large scale, we have a big problem because in the mountains I know that the change in the snowpack is the primary cause of the change in the backscatter. When we go to the flat terrains, Germany and other regions, then there are other reasons which might cause the change of backscatter. So these are agricultural fields. The farmers go out with their trucks and are changing the roughness of their fields. We detect it in the SAR, and that's what we see actually all here. Okay. Then, of course, in the Valley of Po, for example, a unique example, there are these rice fields. They are lowering and higher the water level. We detect this in the SAR image. Would classify this falsely as snow, because we have a change detection. If it's in the right direction, the system doesn't know what is there, but we know it. So we have corrected this. And when we see, for example, this example, these crops are growing and are cut down again and so on. So these are big changes also in backscatter. The roughness of the agricultural fields are changing. From the SAR system alone, we cannot detect this. We have 1 or 2 measurements only. We need additional information. And this ambiguity in these regions, we tried a couple of things, can only be solved when we go or combine it with optical images. So you take an optical image, you make a kind of cloud gap filling, and then of course you know, okay, there is snow, or the change of the backscatter, what the SAR gives me in these regions is there. In mountain regions this is not needed, because there I know that at 3,000 meters there are no farmers cutting their bananas or whatever. We try to extend this in order to check the melt phases from Sentinel-1, and this is a time series of Sentinel-1 actually. So this is the winter period. When the melt starts, it's going up, it's going down the backscatter, and we have 3 different phases. One is the rapid decrease, which is a wet snow, what we just detected. Then we have a this intermediate increase of backscatter, which is the refreezing one. Example would be this. But and then there's a gradual increase of sigma naught at the end of the melting season, when it becomes snow-free, and that would be the big change. With 6 days, we cannot really do this. We tried this, but 6 days sampling, this is really too coarse in alpine regions in order to detect these daily night refreezes. It's not possible. But there's a chance for the future. There's a Earth Explorer 12 candidate mission, which is called Hydroterra Plus. It is a geostationary SAR, so it is totally different than a low orbiting SAR, which is polar orbiting. This SAR system is at 36,000 kilometers, like Meteosat, on the equator. More or less, it's not on a fixed position. A SAR needs some movement, so it has a small ellipse of about 300 kilometers or something like this, which is going within 1 day. And it is not a global mission, but it has the advantage that it can steer to one of these blobs continuously. So it can switch electronically the antenna to switch from one blob to the other, or on the other hand, it can steer really to, if there's an emergency or whatever, the continuous time. And this, of course, would mean that we get every hour or every second hour, how we program the system, we have the chance actually to look to these changes in the backscatter with time, also during the day. We are now looking to a totally different type of processes. This system would help us on this, because I can look to these daily changes of backscatter. Sentinel-1, we can detect weekly changes, or 3 days, 4 days changes if we use everything. With this system, we would have the chance really to check this. It's a C-band radar. I'm not going into. There is one disadvantage of the system. If it's selected as an Earth Explorer, the launch will be 35. So that's it's a long time to go. But it's good for you, so you have time to prepare for that. But when we go now to polar regions, and now I have to speed up, we have this continuous, and that's also from Sentinel-1 or for AceCat, and then we have the winter period with high backscatter, a strong drop-off during the beginning of the melting season, and at the end, this refreezing takes 2 months. And then, of course, and it's continuously, because we're in polar regions, there are not these daily changes of the weather. Once the polar night is coming, it gets slowly colder and colder and colder, and we have really a continuous refreezing of the complete snowpack. After 2 months about, in Antarctica, for example, we are back, we have a completely frozen snowpack on the margins, and this is in principle then detectable. What we can do is we can track, that's the example in Greenland, we can track this melt and refreezing during the day using AceCat data. So applying this method, so it's a time series analysis of backscatter. We have 4 classes. The first one in gray is there is no melt. Then the beginning of this melt is this light blue. Then the wet snow layer, when it's really saturated from the SAR signal. At the beginning of one is the darker bluish. And the yellow one indicates the increase of the refreezing depth during the time. And this is, of course, now a coarser resolution sensor, a scatterometer system of about I think 4 kilometer resolution approximately, but can be also done with the SAR system, of course. we can compare these melt days events with the regional climate models, and there are differences. And this information is important for climate or regional climate models in order to correct their melt events in the model itself, to have some indications. And when we compare, for example, the difference in the melt date between these products I have shown before and the regional climate models for 4 different climate models, so we see that the first is the climate model itself do not agree on each other, and that there is a big difference for the Hirham, for example, which is driven by error 5 against the other models. In general, those regions which are red, this scatterometer-based product has more melt days than the RCM, and the bluish one is vice versa. The margins have to be masked out because this is ice and not snow anymore, and therefore we took it away because the method is not working. It's just to show you what we can use these products. So the input for improving the models, these climate models, it's very helpful, and also to improve these melt processes. What can we do else? We can estimate now, we are focusing actually at the end of this part. So we are looking here now only to this refreezing layer. At the beginning, I can't do a lot because I know melt starts after 5 centimeters at seabed. I don't have any access to the layers below because of the penetration. But at the end, with this refrozen, when I see this gradually increase, and this is a kind of chance what we are just working on is that we can estimate, using this slowly increase in time, to estimate the thickness of this refrozen layer. So it's a time series analysis. We tried this also in the Alps. It's not working because the sampling isn't okay. In the polar regions, it is a little bit, this is during the beginning of the polar night, when the refreezing starts, the sampling is okay on a daily or even 6 days period. And we can estimate this. And for this, we use a backscatter model, and these are 2 simulations at C band, for example. Again, we need some assumptions on the liquid water content. That's the thickness of the refrozen layer. And we see more or less that when the refrozen layer is increasing and increasing, we are going back. But at seabed, we have some saturation, of course, because at a certain amount, the sensitivity goes really bad. And here, of course, so it's about, let's say, I would say here with 1.5 meter of depth, then more or less the seabed saturates. L-band has a less strong interaction with the refrozen layer, and the sensitivity would help. So the aim is now to include the upcoming L-band SAR systems in order to estimate this. And that's a combination of Sentinel-1 and Roselle, but also of NISA, which is coming actually in the very near future, so in a couple of months.
Yeah. Is there a problem with the roughness? When roughness is
Yeah. So okay. So what we are doing is we need. Okay, I have to look for the time, but okay, a very quick answer. The roughness is a problem. So the problem is we are not relying only on the model itself, but for calibrating the model, we are taking the winter period before, and then we can adjust, so include the complete model, especially the grain sizes and so on, of the refrozen snow. So this is what we are doing. Then, of course, during the melt, we need some assumptions on the grain sizes, but we keep it at the same. And then, of course, the assumption is also that the next winter, when everything is refrozen, the grain size will be very similar as the other one. And this is probably the case because when we look for the time series, so we have here minus 2 dB, at the end of the winter period here, we are again at the same level. So in principle, the medium after the summer period is approximately the same. Of course, if there is a big change, this assumption is not holding, but we have no other chance if we have only one frequency. So you have a limited amount of measurements. So we don't have too many degrees of freedom in order to form the model. When we add more frequencies, like the L-band, we have more chances on this. But currently, there is no systematic acquisitions of the data. One example, so this is for the melt, we are using a reference image. We just selected from one season the extremes case what we have. We can adjust the model for this. We use, this is 15th February and 3rd of March, and you see a increase more or less at the end of the melting period. So this is in Antarctica. So March we are going towards the winter period. We see that there's a gradual increase in principle of the backscatter. Applying this method, we can estimate actually the thickness of the different dates. So this is 15th of February. In principle, the thickness is from 0 to about 1 meter, I think. So there is it's almost none. Then we see that land inwards actually, so that would be the sea. The refreezing starts, and then in March it is getting more and more. The nice thing is that a product like this is absolutely unique. There are no data for validating it. So the aim is now actually to go there and do some field measurements and see if this approach actually helps. So that's something what we would actually like to do. Okay. I'm finished now with this course, but maybe I take 2 or 3 minutes for introducing you to the exercise. So you have to split up into 2 groups again. So Gabi will be in one room, I will be the other one. You will get a handout which is at the entrance of your room, a step-by-step one. And the exercise actually what you should do is to generate a Snowmelt area map from Sentinel-1 data. All the data should be on the computer. And then, of course, we are, I hope that we are programming quite quickly because we want to compare and discuss the results using this information from the SAR also with the optical images. There are differences, and it's quite good to understand and discuss how this is working. Which region are we looking at? So we took a region where we have been, so you know this excellently, you have seen all the details there. So Hintertux would be about here, here is Innsbruck, this would be, there are some glaciers in there, height changes are from 500 meters to 3,500 meters, it's topography there, and this is done. The data for the exercise, what you will get is, you have to do it in Snap, all the SAR processing. I'm sure that you are experts on this after this week. Then we have 2 Sentinel images, so we make a simple approach, 2 Sentinel-1 images for 2 days. The 10th of April and 24th of this year is this one with the melting conditions. So for this state, we want to generate the wet snow map, and we choose actually the January 23 as the dry snow map. We know that this is only one image, but calculating these multiple averaging images would take too much time. Then you will have a digitalization model prepared for the region. For comparison and discussion of the results, you will use QGIS, so you can load the exported images from Snap in there. You will get also an optical image, which is already processed as a snow map, and then to discuss and find the differences between your processing and the other ones. The main steps, and you will get this there, so we help you a little bit. So first you have to import the Sentinel-1 data to Snap, you prepare and calibrate the right data, so you do all the processing steps for SAR in principle. We start with GRD data. Then you calculate the ratio images. So here you have to be careful that first these are not amplitude data. You have to work with intensities or radar brightness or backscatter data as power. And they should, when you calculate the ratio, then they should not be in dB, so in natural units. If you calculate in Snap, you have, I think, the option to do this also in dB, then a ratio in dB is the difference. So just take care of this, otherwise you get strange results. Then you have to geolocate the ratio images, then you can detect actually by your own a threshold, so you can use the threshold. So those who were clever had actually looked to these thresholds, I think they were there. But you can look to a threshold which is appropriate actually, according to your opinion, also to detect the wet snow, to make a kind of mask. Then you can generate also the layover and shadow mask. If you are short in time, you can skip this step. This is just to click on it and you have to wait a couple of minutes. This is in principle just masking out some parts where you cannot retrieve it. But okay, normally you do this if it's fast, but if you're short in time, I think, I don't know how fast the computers are, it can take up to a few minutes or 10 minutes, I don't know. But just say, okay, I don't do this step because it's just clicking on the button. And then I think the interesting part will be that to intercompare the wet Snowmelt from SAR with the optical products what we provide you in your folder. And then especially you should look where are the big differences. And if you see big differences, just try to explain for yourself, and maybe we can discuss this also a little bit if we have time. Why are the differences there? Is it because of dry snow, or is it a kind of problem with agricultural fields in the valleys, for example, or what might be the reason for that, to understand it also a little bit. You will get this in your handout for the exercise. And at the end, when you do this SAR snow map, so this is for the discussion, you have a SAR snow map looking maybe like this or similar, and then the snow cover fraction map for intercomparing. And okay, so we wish you good luck for that.